In this presentation, we are going to learn the mutual inductance between two long coaxial solenoids. We are going to prove that M21 is equal to M12. What is M21? Mutual inductance of the second coil with respect to the first coil is equal to mutual inductance of the first coil with respect to the second coil. This equation to be proved. In the case of mutual inductance, we have to take two solenoids. This is the first solenoid. It's a first solenoid, it's a lengthy coil. The area of cross section of the each turn is A1. The number of turns which are used in the first coil is N1. This is the first coil. Now we are going to take the second coil. In the case of second coil, you have to draw like this. The number of turns in the second coil is N2. Okay. And the area of cross section of the each turn of the second coil is A2. So these are all the descriptions. First we are going to derive the expression for M21, that is mutual inductance of the second coil with respect to the first coil to be found out. Later we are going to derive the expression for M12. Okay. So first we will concentrate on which one? M21. How to derive M21? Now this coil, second coil, to be placed within the first coil. Now I am going to draw the new diagram. Look at that. The first coil to be drawn, its area of cross section is slightly bigger than the second coil. Okay, this is coil number 1. Are you clear? To differentiate this, I am using the red pen. The second coil to be placed within the first coil. Are you clear? The second coil to be placed within the first coil. Now the two coils, they are having the common axis. They are having the common axis. Now I am going to draw the common axis for both. I have drawn the common axis for both. That's why this is called as coaxial coils. Are you clear? Why it is called as coaxial coils, coaxial solenoids? So solenoid number 1, solenoid number 2, both the two, clear, they have the common axis. That's why they are called as coaxial solenoids. Now you know about the meaning of M21. What is M21? Mutual inductance of the second coil, mutual inductance of the second coil with respect to the first coil to be found out. For that, what we have to do? We have to supply some amount of varying current through the first coil. I1 is the amount of current that is passing through the first coil. Are you clear? So what kind of current is sent here? Varying current is allowed to pass through the first coil. When varying current is allowed to pass through the first coil, flux will be created here. Magnetic flux will be created in the first coil. Some amount of magnetic flux will be created in the first coil. Since the second coil is placed within the first coil, the flux will be linking with the second coil also. Are you clear? So let's calculate what would be the magnetic field here at the center of both the two coils. Due to the flow of current I1, some amount of magnetic field will be created at the center of the axis. That axis is common for both. Now I am going to write B1. What is B1? B1 is called magnetic field produced inside the first coil. Already we have derived this equation. B1 is equal to mu naught N1 I1. This magnetic field is created within the first coil. What is I1? I1 is the current flow that is passing through the first coil. So this is the magnetic field which is created inside the first coil. Now we are going to calculate the magnetic flux linked with second coil with respect to the first coil. After calculating B1, we are going to calculate pi 21. What is pi 21? When current passes through this coil, what will happen? Flux will be created in the first coil, and some amount of flux is also linked with second coil. Therefore, pi 21 means magnetic flux linked with second coil with respect to the first coil. So this is the meaning of pi 2 1. How to calculate this? Here we have to use the formula. Are you clear? Integral of A2. What is A2? Why A2 is used? Here this is the area of cross section of the second coil. A2 is the area of cross section of the second coil. Magnetic flux linked with which one? A2 area. That's why this is taken here. Can you understand? Here dA is called as a small area. Is it clear? A small area to be taken within this A2. A small elementary area to be taken within this A2. Therefore, the formula is B vector dot dA vector to be written. Are you clear? So this is the formula. Here B vector dot dA vector, in which dA is nothing but small elementary area to be taken in this each turn of the coil. Therefore, B vector dot dA vector is taken. This is the formula for calculating the magnetic flux. Here, this area is clear, that is somehow related with the magnetic field B1. Therefore, you have to write B1. Are you clear? Because of the field B1, with respect to the value of B1, we are calculating the flux. Are you clear? The flux is only because of B1. Therefore, we have to write B1. After that, what we have to do? We have to write this B1 and this dA to be integrated. After integrating, you will get the total area. Therefore, we can write A2. A2 is the area of the second coil, area of the each turn of the second coil. So B1 A2 is the formula. Here you have to understand one thing, that this is the area A2. Here this is called area vector. Okay, in between area vector and A, what is the angle? 90 degree. Area vector is always perpendicular to A2. This is the direction of B1. Are you clear? This is the direction of B1. This is the direction of A2 vector. Angle between B vector, B1 vector and A2 vector is how much? 0. A2 vector and B1 vector both are acting in the same direction. Therefore, theta is equal to 0. So, if it is expanded, what will happen? Here you will get cos theta. Here one cos theta will be here. Instead of theta, substitute 0. B1 A2 cos 0 to be substituted. Understood? Cos 0 value is how much? 1. So finally you will be getting B1 A2 is a formula for flux linked with second coil with respect to the first coil. Here, how many number of turns are there? N2 number of turns are there. Therefore, flux linked with N2 number of turns is N2 pi 2 1. This is flux linked with each turn. Here N2 pi 2 1 means magnetic flux linked with N2 turns of the second coil. That is the meaning. Are you clear? So what we have to do? This part, is clear? This part to be multiplied with N2. N2 B1 A2. In that format we have to write. First I will explain. Clear? This one to be substituted. B1 is already found out. Substitute here. N2 mu naught N1 I1. Instead of B1, I have substituted this factor. What is the remaining thing? A2 is the remaining thing. Could you understand? Now, what is N2? N2 is nothing but number of turns in the second coil. Here, length of this portion is L. Both the two lengths are same. The length of the first coil and length of the second coil both are same. We know very well that small n2 is equal to n2 divided by L. What is n2? Number of turns per unit length. What is n2? Tell me. Number of turns per unit length is called n2. Therefrom we are able to get the expression for n2, capital N2. Capital N2 is n2 into L. So here instead of n2, substitute n2L mu naught N1 I A2. So this is the expression for which one? N2 Y21. This is the expression. Now this one could be written in proper form. How it could be written? This one could be written as mu naught N1 N2 A2 L, and another factor is what is this? I. So this is the expression for N2 pi 2, which is equal to mu naught N1 N2 A2 L I. So this is one of the important expression. Already from the mutual inductance concept, already we have derived one important equation called, what is this? N2 pi 2 1, which is equal to M21 I. This expression was already derived. I will block this two expression, very important. This one was already derived when the initial introductory part of the mutual inductance. This is another important equation which is derived here. So how many equations are there? Two equations are there. Look at the LHS part of both the two equations. In LHS part, N2 pi 2 1 is here. Here also N2 pi 2 1 is there. So therefore we can equate both the two RHS part. I will write it here. M21 I is equal to, actually I1 has to come. Are you clear? When you calculate M21, that M21 is because of the current flow I1. Are you clear? So M21 I1 is equal to mu naught N1 N2 A2 L I1. Are you clear? This is the expression. Are you clear? I1 is the current which is flowing through the first coil. So that must be written proper form. Therefore I1 can be cancelled. So now you are able to get the expression for M21. M21 is equal to mu naught N1 N2 A2 L. So this is the final expression for which one? M21. Now we have found out the expression for M21. Are you clear? Next we are going to derive the expression for M12. Are you clear? Now I am going to derive the expression for M12. To calculate M12, the following procedure to be followed. First I will draw the second coil. Are you clear? Second coil to be drawn. This is the second coil through which I2 amount of current is flowing. The area of cross section of the each turn of the coil to be taken as A2. Are you clear? When I2 amount of current flows, here there will be a magnetic field which is created at the center of the coil. The strength of the magnetic field can be written as B is equal to. B is the magnetic field which is created due to the current flow I2. Therefore, B2 is equal to, why it is called B2? B2 is the strength of the magnetic field at the center of the second solenoid. How to write the formula? Mu naught N2 I2, the strength of the magnetic field is created due to the current flow I2. Therefore, I2 has to come in the equation. V2 is equal to mu naught N2 I2. Here the number of turns in the second coil to be taken as what is this? N2. So these are all the descriptions of the second coil. Are you clear? Now this second coil that is placed within the first coil. Already we have learned this. Are you clear? Now I am going to draw the first coil. The first coil, its area of cross section is slightly bigger. Already I have told. Here the number of turns of the first coil is N1. This is coil number 1. Are you clear? The area of cross section is A1. But you have to understand. Here the thing is, here outside the second solenoid, the magnetic field is 0. Are you clear? Magnetic field is created here within the, which one? Within the second solenoid, the strength of the magnetic field is written. But outside the second solenoid, almost the magnetic field at that point is 0. Are you clear? So the flux is mainly linked only within the area A2. Are you clear? Most of the flux is created only in the area A2, not in the area A1. That is very, very important, because the flux outside the second solenoid is 0. Therefore, there won't be any much flux in this part, that is in the area region of the first solenoid. Therefore, A1 should not be considered, A2 must be considered. Very, very important point. Here the strength of the magnetic field is B2. Strength of the magnetic field outside the second solenoid is almost 0. So the maximum flux is linking only with the A2, not in A1. What is A1? A1 is the area of cross section of the each turn of the first coil. A2 is the area of cross section of the each turn of the second coil. So more flux is linking with, I will draw the diagram here, only then you can understand. This is the each turn of the second coil. Maximum flux is linking with which one? A2. Are you clear? This is the area of cross section of which one? A1. So while calculating the flux, A1 should not be considered, A2 alone must be considered, because almost the magnetic field is 0 here due to the flow of current I2. Are you clear? That is very important. Now I am going to write the formula for flux. Are you clear? What is this? Pi. Pi is the symbol for flux. Pi 12. What is pi 12? Magnetic flux linked with first coil, first solenoid with respect to the second solenoid. How to spell this? Magnetic flux linked with first solenoid with respect to second solenoid. What is the general formula? Integral of, here as I have told earlier, the flux is mainly linked with A2. So what is the formula? Magnetic field B2, it's a vector, and then dA vector. What is dA vector? In this A2, a small elementary region is taken, that is called dA vector. After taking the entire area, this equation, that one becomes B2A2. If you integrate all the dA, what you will get? You will get A2. Are you clear? This is in the form of dot product. Are you clear? Now this one can be written as B2 A2 cos theta must be written. Here angle between B2 vector and A2 vector is 0. Theta value is 0. As I already have explained this. So B2 A2 cos 0 degree must be substituted. So finally we will be getting B2 A2. So this is the expression for pi 12. Are you clear? Now flux linked with N2 number of turns to be calculated. Flux linked with, clear, N1 number of turns to be calculated, because we are going to calculate M12. Therefore first coil to be taken into account. Therefore flux linked with N1 number of turns. Flux linked with N1 number of turns can be calculated by N1 pi 12. Make a note. N1 pi 12 means flux linked with N1 number of turns, because first coil must be considered while calculating M12. N1 pi 12 means flux linked with N1 number of turns in the first coil must be written. So here also you write N1 instead of this pi 12 substitute B2 A2 to be written. Are you clear? Now En1 can be written as it is. We know the expression of B2. Is it clear? B2. What is the expression for B2? Mu naught N2 I2. Instead of B2 it is substituted. A2 can be written here. Are you clear? Next one is here instead of N1. Okay, already we have learned that number of turns. Here N1 is nothing but number of turns per unit length. N1 is called number of turns per unit length, that can be written as N1 divided by L. Okay, this is the formula. From this formula, we are able to write N1 is equal to N1 into L. Okay, so here instead of N1, substitute here N1 L mu naught N2 I2 A2. So this is the expression for N1 pi 1 2. So this is the expression obtained finally. In the previous concept of the introductory part of the mutual inductance, we have got one expression N1 pi 1 2, N1 pi 1 2 is equivalent to which one? M12 I2. Okay, so this is the expression was already derived. Are you clear? This expression was already taught and derived in the introductory part of the mutual inductance. Now we have got two expressions. Two expressions are there, N1 pi 1 2, N1 pi 1 2. So this is the expression obtained from this part of the derivation. This is the expression obtained from the introductory part of the mutual inductance. Look at that, both LHS are same. Both LHS are same. Therefore, RHS can be equated. This one can be taken as first equation, this one can be taken as second equation. I will write it here. Now you write this expression here, M12 I2, which is equal to, what is this? Substitute mu naught, this equation to be written here, mu naught N1 N2 L A2 I2. Okay, this expression is written here, this expression is written on the other side. What can we do now? I2 can be cancelled. So what is the final expression? M12 is equal to mu naught N1 N2 A2 L. So this is the final expression obtained clear in the case of M12. Okay, the previous page we have obtained the expression M12, that is also equal to mu naught N1 N2 A2 L. Okay, in the previous page this expression was derived. In this page we have derived this expression. Look at both the two expressions, both are similar. So finally we can prove that M12 is equal to M21. So this expression is finally proved. It shows that mutual inductance of the first coil with respect to the second coil is equal to mutual inductance of the second coil with respect to the first coil. Okay, this proof may be asked in the essay question. Understood?